Hi everyone, welcome to the second lecture in chapter 12. We're continuing talking about nervous tissue. Today we're going to be looking at action potentials. But before we get going, let's have our not really attendance questions for the day. Regarding voltage, the inside of the cell is blank compared to the outside of the cell. And second, what are voltage-gated channels? So go ahead and try to answer these. And let's see if we came up with the right answer. Both of these actually came from way back in chapter 3 when we were talking about the membrane of the cell, the plasma membrane. And we're going to be talking about these quite extensively today. Regarding voltage, the inside of the cell is more negative compared to the outside of the cell. And what are voltage-gated channels? They were special proteins that opened and closed in response to changes in voltage. So, like I said, both of these are going to be very important for today's lecture. If you are not really comfortable with that, please go back and review that portion of chapter 3 where we talked about these items when we were talking about the plasma membrane, because today we're going to take that information and build on it quite a bit. Now, last class we talked about the structure of a neuron. And before we dive into talking about action potentials and electrical activity, we're going to look at what happens if one of these neurons is damaged and what, if anything, can be done to fix it. So what we see here is from your textbook in figure 12.10, and up at the top it shows a normal, healthy neuron. This is a motor neuron that's connected to some skeletal muscle. And here in the second image, we see what happens if this neuron was damaged at some point along the axon. So the axon has been damaged, and when that happens, then everything beyond the damage site, so everything distal to the damage site, is basically going to wither away and be degraded. And we're going to have macrophages, cells that come in and eat things. They perform phagocytosis. They're going to phagocytize the material here that was damaged. It's also going to phagocytize this decayed part of the neuron, of the axon, until the neuron is much shorter than it was before. Now, the Schwann cells that are in this part where the axon degenerated, the Schwann cells are also going to begin to degenerate. But they reform pretty quickly. Schwann cells can go through mitosis, and all of them don't die. So they're going to restructure themselves, and they're going to form something called a regeneration tube. Schwann cells form a regeneration tube, and it's basically a hollow tube where the axon will eventually regrow. Now, on the other end, where the soma is going to start to swell up, and that's for a few reasons, but one of which is it's starting to produce a lot of the materials needed for this axon to regrow. Now, the axon here, which was shortened, is going to start to sprout some little fibers called growth processes. And these growth processes, some of them are going to grow outward, some of them are going to grow inward through this regeneration tube. And the Schwann cells start to release various chemicals. Some of the more important are collectively called nerve regeneration factors. And the nerve regeneration factors kind of coax the axon to grow through this regeneration tube. The growth processes outside eventually kind of die off. but the axon continues to grow through the regeneration tube until eventually it reaches the end and we reform our synapses with this muscle. Once that's in place, the soma starts to shrink back down to a more normal size. And eventually this neuron is fully regenerated. Now, this can take a few days, this can take a few years, but in some cases it doesn't happen at all. So what is it that determines if regeneration can occur? Well, first, it's going to be, where was this neuron damaged? If the axon was damaged, but the soma remains intact, it's a pretty good bet that this neuron can regenerate. But if the soma is damaged, chances are this neuron is going to die. Why is that? Well, remember when we talked about the structure of a neuron, all of the organelles are up here in the soma. So if the soma is destroyed, then we can't do anything about it, and we can't get mitosis to replace it. So that's why you hear a lot of times if someone breaks their back, maybe they can get better and, recover movement, or maybe they will end up paralyzed and paralyzed for life. It's just a matter of how extensive was the nerve damage. Now, if these soma were destroyed, then that damage is going to be pretty permanent. Also, it's a matter of central versus peripheral nervous system neurons. We have to have Schwann cells for regeneration to occur. There are no Schwann cells in the central nervous system. So if the nerve damage occurs in the central nervous system, chances are we're not going to get regeneration. But if it's in the peripheral nervous system, there is a possibility that we will get regeneration. Okay, so now the rest of this lecture is going to be talking about action potentials and what we had previously called electrical signals. From this point on, we will call them action potentials. Now, let's do a little bit of review first and talk about some terms that we've introduced back in chapter 3. The first is voltage. Voltage, for this class, we can just simply talk about separation of charges. Separation of charges. And that just means that there are going to be some charged particles on one side of the membrane and some charged particles on the other side of the membrane. And once we have that separation of charges, and there's going to be some positives on one side, some negatives on that same side, some positives on the other side, some negatives on that same side, but they're all going to be in different concentrations, and they're going to be held apart by this membrane that lets some of them through and some of them not. And the result is the inside of the membrane is going to be more negative compared to the outside of the membrane. Now, I want to really stress that the inside of a cell is neutral. It does not have a positive or a negative charge. The outside of a cell is neutral. It does not have a positive or a negative charge. But we are simply comparing the inside of this membrane to the outside of this membrane, and the inside of the membrane is more negative compared to the outside. So we have this separation of charges, and that's where our voltage comes from. And again, that came from chapter 3. That's nothing new so far. Now, when we're talking about neurons, we're going to actually give a number to this. We can measure how negative is the inside compared to the outside, and we'll do that in just a little bit. Now, along the membrane, we also have various types of proteins. Various types of proteins. One of them is called a leaky channel. Leaky because They are always open and things can leak through them. But since these are proteins and their shape is going to determine exactly what they do, and they can only do a very specific thing, there are going to be leaky channels for different types of ions. For example, there will be a leaky sodium channel. There will be a leaky potassium channel. So there are leaky channels specific to certain ions, and those leaky channels are always open, and these ions will move freely through these leaky channels. Next, there are voltage-gated channels, and voltage-gated channels open and close in response to changes in voltage. So we said that the inside here is more negative compared to the outside, and we said that we could measure exactly how negative it is compared to the outside. Well, if that number changes, maybe this voltage-gated channel will open, maybe this voltage-gated channel will close. So this voltage determines if the voltage-gated channel is open or closed. Now, real quick, I want to introduce a word that we talked about way back in the beginning of the semester many times, and we're going to use it again in this lecture, so I want to remind you of it. We see the inside as negative compared to the outside is positive compared to the inside. So the two halves of this membrane are different from each other. What's the word for that? Polar. So this membrane is polar, or it is polarized. Make sure you remember that word because we're going to use it again today quite a bit. There's another type of channel called a ligand-gated channel. And ligand-gated channels open and close in response to a ligand. Well, what's a ligand? A ligand is simply a substance that can attach to a protein and cause it to change shape. So another word for ligand-gated channel, sometimes you will hear it called a chemically gated channel. Well, ligand-gated or chemically gated channels open or close in response to something attaching to it. It's kind of like when you put a key in your lock. If you fit the right key in your lock, that lock will open. If we fit the right ligand onto this channel, the channel will open. And finally, we won't really talk much about this, but I want to introduce it. There's something called a mechanically gated channel. And mechanically gated channels open and close in response to physical deformation. So if you press on it, if enough pressure is applied, it will change shape and open or close. That's a mechanically gated channel. We won't really talk about that one, but these others, the leaky channel, voltage gated channel, and ligand gated channel, we're going to talk about quite a bit. So here is a ligand gated channel, just so that you can see how it works. Here it is closed, but if a certain specific chemical attaches to the ligand gated channel, it opens. And once it opens, specific substances can pass through. So let's start to relate that now to electricity and how cells use these to generate and conduct electricity. Well, first, we're going to have to talk about gradients, and we mentioned these back in chapter 2, I believe. There are different types of gradients. There is something called a concentration gradient. Sometimes it's also called a chemical gradient. And concentration gradients or chemical gradients just means there is more of something in one area, less of something in another area. So let's just say there's a whole lot of red dots in this area, but only a few red dots in this area. Well, there is a concentration gradient or a chemical gradient. Let's put a membrane between them. And let's say this membrane is permeable to the red dots. Well, what's going to happen? Well, remember, everything likes to move from high concentration to low concentration. So red dots are going to move from high to low, down their concentration gradient or their chemical gradient. There's also something called an electrical gradient. So let's say there's some positive charges here and some negative charges here, and I separate them. Well, the positives and the negatives are going to be drawn to each other. There is an electrical gradient. One side is more positive, one side is more negative. And sometimes there is both. So what if these red dots had positive charges? Well, there's a concentration gradient moving this way, but there would also be an electrical gradient moving this way because there would be a lot more positives over here than there are over here. So sometimes the concentration gradient and the electrical gradient are the same. Sometimes they're opposite. We'll see what that means here in just a little bit when we draw our picture. But once we have our concentration gradient and an electrical gradient in place, we develop something called an electrochemical gradient. And an electrochemical gradient is what results from both a concentration and electrical gradient together. If that doesn't make sense, don't worry, because we're going to draw a picture here in just a little bit and see exactly how that works. Now we're going to be talking about several ions, and when we talk about ions, what you will need to know is what type of charge does each of these ions have, and where are they in greater concentration, inside the cell or outside the cell. So first, sodium. Sodium is Na+, so it has a positive charge. And sodium is in a greater concentration outside the cell. It's got a high concentration outside the cell and a low concentration inside the cell. Potassium, K+, so it's got a positive charge. It's got a high concentration inside the cell and a low concentration outside the cell. We've got some really large proteins, and the proteins have a negative charge, and they're really big, so they have a lot of negative charge. And sometimes in your book you will see them just called A-. The A stands for anion. They've got a high concentration inside the cell. Calcium, which is Ca2+, so it has two positive charges. And it's got a very high concentration outside the cell. As a matter of fact, it's non-existent inside the cell most of the time. If it is inside the cell, do you remember where it was stored? Calcium inside the cell tends to be stored in the smooth endoplasmic reticulum because it likes to attach to stuff, and we don't really want that to happen. So it's pretty much non-existent inside the cell, and if it is inside the cell, it's packed away in the smooth ER. And finally, chloride, Cl-. It's got a high concentration outside the cell and a low concentration inside the cell. So there are all of our ions. Some of these we're going to talk about quite a bit, some of them not as much, but this is where they are in higher concentration. Now, because of this separation of those ions, and because of just how permeable the membrane is to each of those ions, we get that separation of charges. we get a voltage. And remember, the inside of the cell is more negative compared to the outside of the cell. Every cell in your body is a little bit more negative inside compared to outside. But I also said that once we start talking about specific cell types, we can measure exactly how much more negative it is inside compared to outside. For example, today we're going to be talking about neurons, so we will be able to measure that exactly. Well, whatever the voltage is for a cell while it is at rest, that voltage is called the resting membrane potential. Sometimes it's just abbreviated RMP, the resting membrane potential. That is the voltage of a cell while it is at rest, when it's just doing nothing. And because there is a voltage, because the inside is different compared to the outside, again, we say that that membrane and that cell, it is polarized. It's different on one side than it is on the other side. And that comes from mainly permeability to those ions. How easy is it for those ions to cross the membrane? Well, the easier it is, the more of those ions will cross the membrane. And if we have those charges, like, for example, sodium with his positive charge, if we make the membrane permeable to sodium, more sodium is going to leak through, and it's going to change that voltage because it's bringing positive charges with it as it moves. Same thing for potassium. So how permeable a membrane is to any specific ion is going to affect the resting membrane potential. We've got those ions moving. How easy are they moving? What kind of charge are they taking with them? That's going to affect the voltage. It's going to affect the resting membrane potential. Well, we've got these ions moving. We've got sodium moving across the membrane. We've got potassium moving across the membrane. How do we make sure that they don't just keep moving? How do we make sure that they go back where they're supposed to go? Well, that's our old friend, the sodium-potassium pump. We met him back in chapter 3, and it was his job to use ATP and move sodium and potassium back to where they're supposed to go. So we will see that here in just a moment. Now, the inside of the cell is more negative compared to the outside of the cell while at rest. We've got a resting membrane potential. Here we see a resting membrane potential of -70. Well, that's going to be a number we hear a lot today because -70 millivolts is the resting membrane potential for a neuron. We'll talk about that again in just a minute. -70 millivolts is the resting membrane potential for a neuron. If this was a muscle cell, it would be different. But for this cell, the cell that we're looking at, we're at -70 millivolts while at rest. If we were to somehow make the membrane more permeable to a certain ion, maybe we make that cell a little bit less negative. Well, that's called depolarization. Depolarization just means we become less negative than resting membrane potential. Less negative is a weird way of saying it, I know, because it sounds like, well, more positive sounds a little bit more natural to say, but we actually say it becomes less negative than at rest. It's becoming less polar than it was. It's going back closer to zero. When we make a membrane that is polarized less negative, when we bring it closer to zero, we say that we are depolarizing the membrane. On the other hand, if we make that membrane more permeable to something and it causes it to become more negative than at rest, we say that we are hyperpolarizing that membrane. Depolarization makes it less negative, closer to zero. Hyperpolarization makes it more negative, takes it further away from zero. And we can do that by making the membrane more or less permeable to certain ions. Remember, ions, they have charges. If they are crossing the membrane, they're bringing those charges with them. So if we move more charges or less charges, we can depolarize or hyperpolarize that membrane. Now, if we're looking up here, we can see the dendrite is what we're looking at up here. The same exact thing if we looked at the soma, then we could make this really depolarized or really hyperpolarized. Maybe it's just a little bit depolarized like we see here, or maybe it's even more depolarized, or maybe it's even more depolarized, or maybe it's even more depolarized. Here, this is called a local potential or a graded potential. Same thing for hyperpolarization. Maybe we make it even more hyperpolarized or even more hyperpolarized. Graded potentials or local potentials, they can have a very small magnitude or a really large magnitude. There is no limit to the magnitude. And it can go in either direction, de or hyperpolarized. But the greater the magnitude, the greater the area of effect. Greater or lesser magnitude will have greater or lesser area of effect. Graded potentials are local, but the size of that locality is directly related to the magnitude of change. Let that sink in. The greater the magnitude of change, the greater the area of effect. That's a graded potential. Now, we're going to build on that, and it's going to tie into what we talk about today and what we talk about in lecture number 3. But let's talk about action potentials. Now, graded potentials, what we saw here, it was local. Action potentials, on the other hand, are not. Action potentials move. They do not stay in one spot. Action potentials are going to move along the cell. But let's go ahead and draw an action potential. We're going to see what causes an action potential. We're going to see the steps of an action potential. And the picture that we draw is going to look a little bit different from your book because personally, I don't think your book does a very good job of showing how an action potential works. So let's exit out and get to our whiteboard app. And while you're drawing this, you can pause the video and get this all drawn, but I want to talk about what it is that we see here. This blue membrane is the cell membrane somewhere along the axon of a neuron. To the left of the screen is going towards the soma. To the right of the screen is going towards the axon terminals. The red boxes are different types of proteins. Here, all the way on the left, is a leaky sodium channel. All the way on the right is a leaky potassium channel. And they're leaky, so that means they're always open. And that's what this red line in the middle of each of them is supposed to be. That represents a tunnel passing through. Next, we have a voltage-gated channel. This is a voltage-gated sodium channel. Over here, we have a voltage-gated potassium channel. Now, real quick before I talk about this other guy, look at the voltage-gated sodium channel and the voltage-gated potassium channel. They look really different. The voltage-gated sodium channel has this weird little wrecking ball looking thing. This is called the inactivation gate. The voltage-gated potassium channel doesn't have that. So voltage-gated sodium channel, in addition to just opening and closing in response to change in voltage, it also can become inactive. So it can be open, it can be closed, or it can be inactive, and we'll see what that means as we draw. The voltage-gated potassium channel does not have that. It can be open or it can be closed, but it cannot be inactive. Right now, both of them are closed because they don't have that red line going down the middle. Now we also have the sodium-potassium pump. And the sodium-potassium pump, I've drawn some ATP down here next to it because it uses ATP. Now, before we talk about this graph down here and talk about things like what voltage we are at, I want to talk about where we, or things that are always going on in this cell. So, regardless of what else is going on in the cell, there's a few things that are always going on. And first, we have sodium that's going to move through its leaky channel. But which way does it move? Let's look at gradients. Sodium has a high concentration outside the cell, and this should be a low concentration inside the cell. And we said the inside of the cell is negative compared to the outside. So sodium is coming into the cell. And it's coming into the cell down its concentration or chemical gradient. It's also coming down into the cell down its electrical gradient. Concentration from high to low. Electrical because his positive charge is attracted to the negative inside the cell. So his concentration gradient is inward. His electrical gradient is inward. And now, adding them together, we could say his electrochemical gradient is inward. Over here, let's look at potassium. Potassium has a high concentration inside the cell and a low concentration outside the cell. But he's got a positive charge, and the inside of the cell is negative. So now we've got a situation where his concentration gradient is outward. His electrical gradient is inward. So we have some potassiums moving out of the cell. We have some potassiums moving into the cell. But more potassium is going out than coming in. So I'm going to erase the dotted line inward. It's still happening. It's just more is leaving than is coming in. So we're only going to talk about potassium leaving the cell. Potassium has an electrical gradient inward. It has a concentration gradient outward. So his electrochemical gradient in this case is outward because more potassium goes out than comes in. Now we've got sodium constantly leaking in and potassium constantly leaking out, regardless of what else is going on. We need to make sure that this gradient stays in place for both potassium and sodium. So how do we make sure that those gradients stay in place? The sodium-potassium pump. Sodium-potassium pump takes 3 sodiums and 2 potassiums. Takes the sodium and pushes them out, takes the potassium and pushes them in with 1 ATP. Then it gets another ATP and it does it again. It gets another ATP and it does it again. As a matter of fact, the sodium-potassium pump uses more ATP than any other thing in your body because they are in every cell in your body and they are constantly working. So they use a lot of ATP. And their job is to create and maintain these gradients for sodium and for potassium. Now, because of these gradients, we end up with a cell that is more negative inside compared to outside. We said this is a neuron. We're somewhere along the axon. So it's not just more negative. We can measure it, and we find that it is negative 70 millivolts at rest. Negative 70 millivolts at rest. Now we've got everything in place. Let's relate this to an action potential. So how does an action potential work? Well, something off screen, up in the direction towards the soma, is going to happen. And right now, that's all we're going to say about it. We're just going to say something up screen happens. We'll see what that something is at the very end. Something happens that causes this negative 70 millivolts to start to rise. It goes from negative 70 up to negative 65. Maybe it gets to negative 60. And if that's as high as it gets, nothing at all happens. Nothing happens. But if it keeps going, if it gets to negative 55, then there's no stopping everything that comes next. If we get to negative 55, this number is called threshold. If we get to negative 55 inside the cell compared to outside the cell, then nothing can stop what happens next. Action potentials, we say, are all or none. That means if we don't get to this magic threshold number, then we don't get an action potential. If we do get to this magic threshold number, then we get an action potential and there is no stopping it. It will continue to happen. That's all or none. So let's relate that to this graph of an action potential down here at the bottom. This graph is in a few times in your chapter. The one that I have displayed here is on is on figure 1216. There are other versions of it throughout the chapter. So far, we have looked at rest. See if I can draw on it. We have looked at rest right here. We have started to look at this rising part. And if we get to negative 55, we get to threshold, then something is going to happen. We're going to have what I call some magic numbers. And at each of these magic numbers, something important is going to happen. If we get to threshold negative 55, then what's going to happen first is our voltage-gated sodium channel opens. So let's look at the consequences of this opening. First, we have now another path for sodium to come into the cell. He's still going to come down his concentration gradient. He's still going to come down his electrical gradient. He's going to do the exact same thing, but a better way to say it is we have just made this membrane more permeable to sodium. Remember permeability. We have just made the cell more permeable to sodium. So sodium is going to continue to come in down the leaky sodium channel, but, let me do this in black ink. He's going to continue to come in through the leaky sodium channel, but he's also coming in through the voltage-gated sodium channel. So what happens? Well, now we're going to have a very sharp rise on our graph because sodium's continuing to come in as it was, but he's coming in at a faster rate because we are now more permeable. More sodium is coming in than was at rest. What happens when sodium comes in? He brings his positive charges with him. So we're making the inside of the cell less negative, more positive. What's the word for that? Depolarization. So this rising part of the graph is depolarization. What happens to our voltage number over here? Well, it skyrockets. It goes from negative 55 all the way up to positive 30. We started at negative 70, resting. We got to negative 55 threshold. Now there's no stopping everything that we're drawing. It shoots up to positive 30. And this is where our next magic number is. At positive 30 millivolts, a few really important things happen. First, our wrecking ball, our inactivation gate, is going to slam shut. It plugs the opening. So when that happens, sodium cannot come through anymore. Sodium continues to come through the leaky channel, but it can no longer come through the voltage-gated channel. Now, the voltage-gated channel is still open, it's just inactive. It's going to start to close, but the closing process is really slow. It's slowly squeezing shut. And as it's slowly squeezing shut, sodium is still trying to come through, but it can't because the exit is blocked by this inactivation gate. Something else happens at positive 30 millivolts, and that is the voltage-gated potassium channel opens. What happens when the voltage-gated potassium channel opens? Well, we've just made the membrane more permeable to potassium. So potassium continues to leak out through the leaky channel, but now he also will go out through the voltage-gated potassium channel, taking his positive charges out of the cell with him. So, back on our graph, why don't we continue to rise? Well, because of the voltage-gated sodium channel. Why do we start to see this drop? Well, because potassium is leaving the cell at a faster rate. We made the cell more permeable to potassium. Once we get back, well, first let's look to see what happens to our number here. It goes from positive 30 and it starts to drop. How far does it drop? Well, back to rest, back to negative 70 millivolts. Once we get to negative 70 millivolts, our voltage-gated potassium channel starts to close. But what's missing? We don't have an inactivation gate. So it starts to close, but it's a slow process. Potassium continues to trickle out. Potassium continues to trickle out, overshooting. We go beyond this negative 70. We actually get down to about negative 90 millivolts. And this negative 90 millivolts is because we overshoot due to this voltage-gated potassium channel being slow to close. It doesn't have an inactivation gate. So let's look at our graph. We're dropping, we are repolarizing. Because the voltage-gated potassium channel is slow to close, we overshoot. So we get hyperpolarization. The time from negative 70 down to about negative 90. Eventually, this closes. Once it closes, the sodium-potassium pump is busy resetting everything. We come back up to resting potential. We bring our negative 90 back up to negative 70. And we're back at resting membrane potential. Now, while all this was going on, while the voltage-gated potassium channel was open, and right around the time we got to rest before hyperpolarization, the voltage-gated sodium channel finished closing, and the inactivation gate dropped back down. And we are back exactly where we were to begin with. So here in this local area, we had something called an action potential. And an action potential, all that means is we had a brief reversal of charge across the membrane. We went from more negative inside to positive and back to negative. A brief reversal of charge across the plasma membrane. Now, let's tie this into what happens next. Well, what we've drawn here actually happens thousands and thousands of times across along the axon. Let's draw kind of a neuron up here at the top. Here's the soma, here's some dendrites, here's a long axon. Well, what we have drawn here is a very small location right there. And this whole thing repeats thousands of times along the axon. So just to the right, of what we have drawn here, it's going to repeat. And when we got to our positive 30 right here, well, some of that positive charge starts to spill over just beyond what we see on our screen here. And just beyond what we see on our screen here, it's at negative 70. But it starts to rise from negative 70 to negative 65 to negative 60, and then it gets to negative 55 threshold, and it repeats. And then it repeats right here, and it repeats right here, and it repeats right here. So it's like we knocked a domino over, and that domino knocks over the next domino, and it repeats all the way down until we get to the axon terminals. But what was it that caused it to happen here in the first place? Well, when I said something happened up towards the soma, just off screen, it was everything that we just drew happening right there. So once it happens at one point along the axon, it continues along the length of the entire axon until we get to the very, very end. Okay, so I know that that is a lot of information, and I really suggest watching this a few times, this part, but we're not quite done yet, so let's go back and wrap up just a little bit. But again, watch that part that we just drew several times until it starts to sink in, because it's really important. It's going to come back in muscles, and it's going to come back next semester in the heart. So here's kind of a graph of some action potentials. Each one of these raised lines represents an action potential. Here's one, here's one, here's one, here's one, and then here's some a little bit faster. What is this showing us? This is showing us if we have a stimulus. Maybe we have a really weak stimulus and we don't get an action potential that develops from it. Maybe we have a stronger stimulus and we get some action potentials. Maybe we have an even stronger stimulus and we get some more action potentials. What these graphs are showing us is the relationship between the intensity of a stimulus versus the action potentials that develop. Every action potential in every neuron in your body looks exactly like the graph of what we just drew. It goes from -70 up to +30 and back. If you briefly touch your skin, or if you push on your skin, or if you poke your skin with a nail, well, you're going to have the same action potential magnitude. When we have a stronger stimulus, the action potentials do not have stronger magnitude or stronger amplitude. Here we can see they're all going up to +30. The stronger stimulus produces more frequent action potentials. Here, weak stimulus. Here, strong stimulus. On the strong stimulus side, we have more frequent action potentials. The neuron is sending an electrical signal very slowly versus the neuron is sending action potentials very frequently. That's the difference. So if you just lightly touch your hand versus if you push on your hand, lightly touch, the neurons in your hand are sending action potentials pretty slowly. If you push on it, then it's going to start sending action potentials pretty frequently. And that's how your brain interprets a small stimulus versus a very strong stimulus. Now, even with really strong stimuli, we run into kind of a speed limit. Neurons can only send action potentials at a certain frequency, after which they cannot send more frequent action potentials. And that's because of something called refractory period. So here's our action potential graph that we just saw. Here we're at rest, here we're rising towards threshold, we reach threshold, depolarize, repolarize, hyperpolarize, and back to rest. We can make this happen faster. We can make it happen faster and faster and faster, but we cannot make it happen faster than a certain speed limit. Why is that? Well, because during this area right here, from the time we reach threshold up until the time we come back to rest the first time, between these, so during this red shaded area, we're in something called the absolute refractory period. During the absolute refractory period, even with a really strong stimulus, we cannot get another action potential to occur. That's because the voltage-gated sodium channel is still inactive and the sodium and potassium are still not reset enough that we could actually carry out another action potential. Now, during this hyperpolarization phase, we have something called a relative refractory period here in yellow. Now, during this phase, we can get another action potential if it is a really strong stimulus. If the stimulus is strong enough, then we can get another action potential during the relative refractory period. But during the absolute refractory period, we cannot get another action potential regardless of how intense the stimulus is. Now, let's talk about something called saltatory conduction. As part of the self-study, you learned about Schwann cells and myelination. And you learned that the myelin, there was going to be some Schwann cell wrapping an area of the axon, another Schwann cell wrapping an area of the axon, and a gap called a node of Ranvier in between them. In a myelinated axon, that is going to be the case along the entire axon. And not all axons are myelinated, so we're just talking about myelinated axons. Remember, myelinated axons conduct action potentials faster than unmyelinated. And that's going to be because in this area right here, covered by a Schwann cell, it's insulated. Those proteins that we drew in our drawing earlier are only here at the nodes of Ranvier. And then here, there's nothing. And here, there's more of those proteins. So the action potential graphs, or the whole thing that we just drew, is happening here at the node of Ranvier, here at the node of Ranvier, and then here at this next node of Ranvier. What we get is something called saltatory conduction. When we looked at one of these axons, it is as though the action potential is jumping from one node to the next. And this jumping happens really, really quickly. In unmyelinated axons, the action potential travels the length of the entire axon without jumping. So if we're only looking at the nodes of Ranvier, it's as though the axon itself is shorter because we don't have to worry about this area covered by a Schwann cell. That's why a myelinated axon conducts an action potential faster than an unmyelinated axon. Now, since there are no action potentials that occur here where the Schwann cells are, there are none of those proteins that we drew. Now, let's relate that to a disorder called multiple sclerosis, or MS. Multiple sclerosis is an autoimmune disease, and autoimmune disease just means your own immune system sees some part of your own body as something foreign and it starts to attack it. In multiple sclerosis, this myelin, the Schwann cells that make this insulation, are seen as foreign. And your immune system attacks them and they get destroyed, exposing this part of the axon. And what happens is the action potential does not get triggered to jump. Instead, it starts to travel through. But since there are none of those proteins along this area, then the action potential actually fizzles out before it can get to the next node. And that way the action potential never makes it the length of the axon. Instead, it dies out. And what we end up with in people with multiple sclerosis is some of the action potentials make it the length of the axon, some of them do not. And we get kind of jerky movements, or in some cases, paralysis. That is why, or that is how multiple sclerosis comes about. And finally, I want to talk about local anesthetics. Local anesthetics are an injection that you can get, most commonly we can think of at the dentist office. When you go to the dentist office and they give you an injection in your gums, that's a local anesthetic. If you've ever gotten stitches before they start inserting the stitches, they'll give you a shot in the area where the cut occurred, and that is a local anesthetic. Local anesthetics just block sensation in a very local area, as opposed to putting you to sleep, which is a general anesthetic. So how do local anesthetics work? They actually work by inhibiting voltage-gated sodium channels. They inhibit voltage-gated sodium channels. So how does that cause anything? Well, think back to our drawing. Let's actually go back to our drawing. If we go back to our drawing, the voltage-gated sodium channel is what opened at threshold. He's the guy responsible for the entire action potential. If he never opened, we would never get depolarization. We would never get repolarization. We would never get hyperpolarization. So it's the voltage-gated sodium channel that kind of made the action potential happen in the first place. He was the first player to go. If we take him offline with a local anesthetic, then we don't get an action potential. And no matter what kind of sensation, whether it's cold or hot or pain, any sensation at all it is an action potential. So by blocking the voltage-gated sodium channel, you are essentially blocking pain until that local anesthetic wears off. All right, so that's going to be where we stop for today. I know this lecture was a little bit more intense than some of our previous lectures. I really encourage you to watch that action potential drawing a few times, draw it out yourself a few times. That way, it really, really sinks in. It's important that it does sink in. So if it doesn't, please ask questions. Please watch the video a few times. It does come back. And when it comes back, you have to understand it at that point. And next time, we're going to talk about synapses and what happens when we get to the end of the axon. How do we continue that electrical signal? All right. Take care, and let me know if you have any questions.